Welcome to another podcast. In this episode, we're going to be taking a look at the critical points, extreme value theorem, mean value theorem, something called the closed interval method. It's going to be a pretty long, but it's going to be over an hour probably, pretty long lecture today. This is all of the lecture material for this week. It's all the material that you need to get ready for the quiz on Friday. Friday is Good Friday, so the quiz is already up as of the time of the recording of this video, so hopefully you can get this knocked out either on Wednesday or Thursday. That way you don't have to actually do anything on Good Friday, and hopefully your Easter weekend will be off to a good start. So blessings to you and your family wherever you guys are. I hope things are going well for you. I hope the exam went okay for you. I know we had to do a thing where I had to switch out and make two different parts of the exam, but I think that was probably going to be easier on everyone than continuing with it the way we originally had it. All right, at any rate, let's talk about the things for this week here just real quickly. The announcements. You've got your lecture videos. This video will go up today in just a little bit, and then you'll have the lecture notes. We are in section 4.1 to 4.2. And you do have a quiz that's due this Friday. So it's a pretty light week. You'll have two homework sets as well. One for section 4.1 and then a really tiny one for section 4.2. So really it's just kind of like one homework set this weekend. Don't work on those on Easter. Spend Easter with your family. Get that knocked out before this weekend. And hopefully that'll go well for you this week. All right, let's take a look at the notes together. So we're going to start with what is probably the most important thing for the rest of the course, and that is almost every single problem we look at from now to the end of the course starts by having us find a critical point. So remember, the definition of a critical point is a value, let's call C, in the domain of the function, such that it's a place where the derivative is equal to 0 or the derivative does not exist. That's our definition of a critical point. So I'm going to calculate the critical points of this function and then figure out which of these it is. If you'll pause the video for a second, try it on your own, and then come back and look at what we did. Come back and look at the solution, see if you got it right. All right, if you haven't paused yet, please do so. We're going to start by taking the derivative of this function, which would be 4x cubed minus 16x. We want to set it equal to 0 to find critical points. There are no x values here where the function is undefined. If we factor out a 4 and an x, that leaves us x squared minus 4, so x is equal to 0. Or if I set this term equal to 0, then x is plus or minus 2. So it looks like we have three critical points altogether. We have negative 2, positive 2, and 0. All right, similar question here for example 2. We're going to calculate the critical points of this function. Once again, I will ask you to pause the video, try it on your own, and then we'll take a look at it together. All right, if you haven't paused the video yet, please do so. We're going to take a look at the solution together. So we're going to start off by taking the derivative of this. And this is a problem that will require chain rule. So we're going to do power rule first, bring the 1/3 down. So this will be 5/3 x squared minus 1 to the subtract 1 from the power. It's now negative 2/3 times the derivative of the inner function, which is x squared minus 1. So the derivative of x squared minus 1 is 2x. 2x times 5 makes for 10x. X squared minus 1 to the negative 2/3. And you should be very careful here because this is a negative exponent. I know this term is in the denominator. So realistically, this function looks like the following. It is a cube root of x squared minus 1 squared. Remember, The way that this works is the numerator of the power is the power of the function, and the denominator is the root, and because it's negative, they're both in the bottom. So I have this derivative. I'm going to set it equal to 0 to find my critical points. If you have a fraction, the only way a fraction can be 0 is if the numerator is 0. So we're going to solve the numerator equal to 0. So x equal to 0 is for sure a critical point. But remember, the definition of a critical point says it's any place where the derivative is 0 or undefined. So if I look here at the denominator, x squared minus 1, when it's equal to 0, the denominator will be 0, which means that the derivative will be undefined there. And x squared minus 1 is equal to 0 anytime x is plus or minus 1. So we have two more critical points to consider, b and f. So hopefully you got all three of those. If you just got x equal to 0, you need to make sure that you're looking for places where the derivative might be undefined. All right, let's do another one. What are the critical points of the function 1 over x plus natural log x? So I'll pause here, let you try it on your own, then we'll take a look at it together. All right, if you haven't done so already, please pause the video and try it. The derivative here is pretty straightforward. The derivative of 1 over x is minus 1 over x squared. I'm just treating 1 over x as x to the negative 1 and using power rule there. The derivative of natural log is 1 over x. My recommendation is if you're looking for critical points and you have rational functions like this that are added or subtracted together, that you should get a common denominator and combine them. So the common denominator for the second term here is to multiply the top and bottom by an x. And so if combined, you'll have negative 1 plus x over x squared, and we're going to set that equal to 0. Once again, the only way the fraction can be 0 is if the numerator is 0. So that would be x equal to 1 is a critical point for the numerator. And I also look and see that the denominator would be 0 when x is 0. However, I do want to remind you part of this definition of critical point here is f prime of c does not exist, but the number c had to be in the domain of the function to begin with. So if you look at example 2, we found that 1 and negative 1 were critical points because you could plug 1 and negative 1 into this function and get an answer. But yet in the derivative they were undefined. Here in this example, however, 0, it looks like when x squared is 0, which is when x is 0, it looks like that should be a critical point. So critical point question mark. It looks like that should be the case, but the definition of a critical point is the point had to exist in the domain of the function to begin with. And you cannot plug x equal to 0 into this function on either one of these. 0 is not a part of the domain of the function to begin with, so it's not a critical point. So only x equal to 1 is a critical point here. You can see x equal to 0 is not even among the answer choices. All right, so hopefully you got that one correct as well. All right, so like I said, every question from here to the end of the course, almost all of them are going to start with the first step you should do in solving the problem is finding the critical points. So this is a very important skill. I encourage you to go into section 4.1. There are some problems in section 4.1 that are just finding critical points. I suggest you do the all the odds for those as just practice for this. All right, so this brings us to an important theorem. It's known as Fermat's theorem. It says if a function has a local max or min at c, and if the derivative exists at c, then the derivative is 0. In other words, you can think of it this way. Anytime a function has a max or a min, so f of x has a max or a min, that automatically implies that the derivative at the max or the derivative at the min is 0. So anywhere you have maximums or minimums in your original function, the derivative at those points is 0. Now the question is, does it work in reverse? So this is the true-false question I'm asking here. In other words, if I have a point, so this is just any point in the domain of f, which means that this is a critical point. So if I have a critical point, do I automatically know that f of c is a max or a min? Do I automatically know that? So this one we know. This is what Fermat's theorem states. This one is always true. Right? So maybe write it this way. If f at c is a maximum or f at c is a minimum, then I automatically know the derivatives at those points are 0. But can I reverse it? In other words, if the derivative at a point is 0, does that automatically imply that that point on the original function is a max or a min? So I give you a second to think about it. Pause the video here, commit to an answer, then we'll talk about it. All right, if you haven't committed to an answer yet, you should do so. We're going to talk about it. The answer here turns out to be false. I'll give you a counter example, and it's the counter example that you should always remember for this. For the converse is called the converse of Fermat's theorem. So the counter example is this. Consider the function x cubed. We all know what the graph of x cubed looks like. So here's the graph of x cubed, something like this. All right, what is the derivative of x cubed? Well, so this is false. The derivative of x cubed is 3x squared. Okay, so at x equal to 0, if this is f prime, don't we have f prime at 0? Isn't f prime of 0, 0? So we have a point in the domain of the function that's equal to 0, so that point is a critical point. Is it a max or a min? So if I look at the graph f at 0, is this a max or a min? Well, no. If you look over here at x cubed at 0, this is neither a max or a min. Turns out that it's an inflection point. So this is a place where the second derivative is also equal to 0, and that's what's causing this to not be a max or a min. So the first implication here is always true. If you have a max or a min at a point, that point is a critical point. If you have a critical point, it doesn't necessarily imply that that point is a maximum or a minimum, and your counterexample to that is x cubed. So while this can be true, this is not always true, and my counterexample is x cubed. All right. So the main method that you're going to be tested on in the quiz this week, and the main method for the lecture today, is something called the closed interval method. It allows us to find all of the absolute maximum and minimum values, which another term that we often use for this is extrema, extreme values. So extrema is the plural of extreme in this case. So extrema, to find the absolute extrema of a continuous function f of x on a closed interval from a to b. So what you do if you want to find the biggest value a function has on a closed interval is you take all of the critical points in the interval, the open interval, you take the endpoints and you test critical points and endpoints. Because if you're going to have a max or a min, they have to occur at the critical points. That's what Fermat's theorem says. So you know that if you test the critical points, then you're potentially finding local maxes and mins, right? And if you're testing the endpoints, well, the endpoints are the only other points where you might have a maximum or a minimum on a closed interval. So you test all of them. The biggest number is the maximum. The smallest number is the minimum. All right, so we'll work through this example together. We're going to find the absolute extreme values if they exist for this function, and it's very important that you take note of the interval here. We're on the interval from -1/2 to 3. We're going to find the critical points and test the endpoints, and then we'll also look at this in Desmos. So our function is 3 plus 2x minus x squared to the 1/2 power because it's the square root. So the derivative of this function would be 1/2 3 plus 2x minus x squared to the -1/2 times the derivative of the inner function. So this is the inner function's derivative here is 2 minus 2x, which is 2 times 1 minus x. And you can see that the 2 that's here in the denominator is going to cancel with this 2 that'll be in the numerator. So when I put it all together, you'll have 1 minus x in the numerator. And in the denominator, you'll have the square root of 3 plus 2x minus x squared. All right, so this is the derivative of our function, and we're looking for critical points here. So the question is, do we have a critical point? So we're going to set this equal to 0, which means we're going to set the numerator equal to 0. So x equal to 1 is potentially, well, it is a critical point. Are there any other critical points on the interval? Well, the thing that you have to look at here is the denominator. Is it possible that the denominator has any points that make it 0? Because the original function is valid for any values as long as this thing is not negative. If you look at the original function, it's, let's see, does this factor 3 plus 2x minus x squared, 3 something, 1 something. So if it factors, we need positive x minus x. So minus x plus 3x gives 2x minus x squared. That looks good, yeah. So this would be 3 minus x, 1 plus x. You can clearly see that the values that would make this thing 0, so you've got this in the denominator. The values that make this 0 are x equal to 3 and x equal to -1. Now, you should double check that -1, 3 is out, by the way, because, well, 3 is an endpoint, so we're going to have to test 3 anyway. So I'll go ahead and include it for now. You should also check, by the way, that 3 is an okay value to plug in, but it has to be because it just makes this square root of 0. So at x equal to 3, the original function's defined. What about -1? Well, -1 isn't on the interval. So I don't really care about -1 for the purposes of this problem. So I'm just going to exclude it. Just say not on the interval. Okay. So we have 2 critical points. We also have 2 endpoints. So the points that we're going to test, I'm just going to create a little table here. This is where Desmos can really help us. So the points that we're going to test are the left endpoint, which is -1/2. The first critical point here, which is at 1. And then the right endpoint, which is at 3. So we're going to be testing those 3 values. Okay, this is where Desmos can pay great dividends. So let me just bring up Desmos real quick. And what I'm going to do is plug my function in. The original function that we had was the square root of 3 plus 2x minus x squared. And we're only considering this function on the interval from negative 1/2 less than or equal to x less than or equal to 3. So this is the function that we're considering, and you can see the points on here, but I'm just going to create a table of values real quick. So the first point is x equal to negative 0.5. So negative 0.5. Y1 here is f of x1. Okay, so the function value at x1. The next point is 1, and the next point is 3. And you can see how Desmos puts all those points into place for us. The largest of those points is at 1. So there's my absolute, that's the largest value on the interval, is the value 1, 2. Make that a little bit bigger so it's easier to see. The largest value on the interval is 1, 2. The smallest value, so the smallest y value is 0, and that occurs at 3. So what you would do if you were answering this question, so the values that we had were, this turns out to be the square root of 7/2, although you could get the decimal, it's like 1.33 something. Evaluated at 1 turned out to be 2, and evaluated at 3 turned out to be 0. So the absolute max, largest y value, is here. We have an absolute max at the point 1, 2. And we have an absolute min at the point 3, 0. All right, so this is the closed interval method. Each of the examples we look at are going to be just like this. We're going to take a function, find its critical points, test the critical points versus the end points. The largest y value is the max, the smallest y value is the min. All right, so if you look at this example, we already found the critical points for this example earlier. So if you look 1 over x plus natural log of x right here, we found that the critical point, the only critical point for this example is x equal to 1. So we know that the critical points for this problem are x equal to 1. We know that the endpoints for this problem, we're going from the interval from 1/2 to 4, so x equal to 1/2 and x equal to 4. So we're going to test x versus f of x, where x is 1/2, 1, and 4. And we're going to plug those into Desmos and see what the values are here. Get these to show up side by side. There we go. Okay. So our function here has changed. It is 1 over x plus natural log of x, and it's defined on the interval from 1/2 to 4. All right, let's zoom in on this a little bit. So there's our graph. At the point 1/2, the function value is 1.30685. So 1.30685. At 1, the function has a value of 1. And at 4, the function has a value of 1.636. Okay, so we're looking at this. We know that the largest y value is at 4. So my absolute max is at the point 4, 1.6363. My absolute minimum is here at 1. That's the smallest y value. It's at the point 1, 1. When you give me maximums and minimums, give them to me as an xy coordinate. So it's the coordinate point where the minimum or maximum occurs. You can clearly see here, 1, 1, that's the smallest. That's what we call a local minimum. Locally, it's the smallest point on the interval. It's also the absolute lowest point on the interval, so it's also an absolute minimum. And then the highest point, or the largest point on the interval, is the right endpoint, which is at 4. So there's my absolute min and my absolute max. All right. So sometimes this can be more difficult than you might think. And one of those times is when our problem involves trigonometric functions in some way, because you can get multiple critical points with trig functions. So I want to illustrate that with this example. So we've got our function p of t. This is modeling the population of an insect colony. Population numbers are measured in thousands here. And we're going to look at this over the first 4 months and see what the maximum and minimum values of the population are. So what can become tricky about this example is finding the critical points. If you can find the critical points, this actually turns out to be a really easy problem. So the derivative of this is fairly easy to find. The derivative of 3t is just 3. The derivative of sine is cosine, but you have to multiply by 4 because of chain rule. So this would be 3 plus 4 cosine 4t. And then the derivative of 100 is 0, so it doesn't show up. So we're going to set this equal to 0. Now here's where trig class comes in. I'm trying to solve a trigonometric equation equal to 0. So it's like any other equation up to a point. So we get 4 cosine 4t is negative 3. Cosine of 4t is negative 3/4. So 4t is cosine inverse of negative 3/4. And here's where you need to be careful. Let's think about our unit circle for just a second. Not so much a circle, it's an ellipse. There we go. So let's think about our unit circle for just a second. We have an angle for cosine, right? Okay, so we're looking at an angle which gives me a cosine. So cosine of some angle is negative 3/4. Okay, first off, cosine is negative over here, since cosine is x length on the unit circle. Cosine is negative over here. So there's this angle here. I'll call it theta 1. And cosine of theta 1 at that angle is negative 3/4, right? So this distance right here is negative 3/4. Now, is there another angle that also has a cosine inverse of negative 3/4? The answer is yes. I can look at this angle. So if we construct this ray right here, I can look at this angle instead, which I'll call theta 2. And that angle also has the same x distance on the unit circle. So cosine of theta 2 would also be negative 3/4. Now, what is your calculator going to tell you, and then how do you adjust for the calculator's value? That's the important part, okay? So let's look at what Desmos is going to tell me when I plug in cosine inverse of negative 3/4. All right, so let's ask it cosine inverse, which is arc cosine of negative 3/4. Okay, it's giving me the value 2.418. So I've got for t is equal to, the first value it gives me here is 2.41885. Okay. So let me shorten that a little bit. 2.418, let's just do 9. Okay, so that's, which of these angles did we find? So pi is 3.14, so we're short of pi radians. So we found the quadrant 2 angle. So 2.4189, that's the quadrant 2 angle. This is our theta 1 angle. Okay? Now, I know that I will keep getting solutions as I go around the circle, right? So additionally, I get an answer for every multiple of 2 pi. So say k equal to 0, plus minus 1, plus or minus 2. Every multiple of 2 pi will give me an answer. Okay, because I'll just keep getting that same angle over and over and over again. Okay, what about theta 2? Well, theta 2 is this angle here. How do I find that value? Well, if you wanted to find this value here, what you could do instead is what? It's 2 pi minus the angle we just found, right? Because theta 2 is really just theta 1, but it's starting going from the opposite direction, so it's starting at not at 0 and going forward, it's starting at 2 pi and going backwards. So theta 2 is nothing more than 2 pi minus theta 1, which is 2 pi minus 2.4189. And if you take that, you get theta 2, which is 3.8643, let's say. Your calculator is not going to give you that answer. It's going to give you the first positive answer around the unit circle. It's not going to give you this one. But we need both to do this problem. So the other angle, theta 2, is 3.8643. Plus all of the times we achieved the same angle by going multiple times around the unit circle. All right, so we've got two sets of solutions for cosine inverse of negative 3/4, and in particular, I should divide through by 4 now, okay? So if I divide through by 4, then I've got t is equal to, this is 0.6057, plus I also divide this by 4, so 2 pi divided by 4 is pi halves, so plus pi halves k, where k goes from 0, plus minus 1, plus minus 2, and so on. And then the next one is 0.9661 plus pi halves k. And where I'm getting these from, just once again, I'm dividing both sides of this equation by 4. I'm trying to solve for t. So when I divide by 4, I get pi halves k here as well. And so there are our solutions. These are our critical points. There are an infinite number of them. Now, but there aren't infinitely many on our interval. So be reminded here that our interval is only the first 4 months, which would be from 0 to 4. So what I'm going to do in terms of testing values is I'm going to write down every point until we're out of range, right? So what I mean by that is if k is 0, what are our critical points? Well, they're t equal to 0.6057, t equal to 0.9661. Okay, neither of those critical points is outside the interval from 0 to 4. What if we went an additional time around the circle? So say k equal to 1, you wouldn't do -1 because that would give you negative critical points, and this is a positive interval. So plug in k equal to 1, so we're going to go further around the circle, find the next theta1 and theta2. So basically I'm taking k equal to 1 in this formula, so I'm going to add pi halves to the one we already have. Let's see, if you do that, you will get 2.1755. And the other one, if you add pi halves to it, is 2.5369. So these are both still on the interval. Okay, what if you did k equal to 2? So plugging k equal to 2 in, so now I'm k equal to 2, the 2's cancel, I'm adding pi to the one I already have. So this first one would be 3.7463. And then if I add pi to the second critical point here, I will get 4.1077. And it's at this point that I stop because this critical point is larger than the interval. So this one's outside the interval. And even though there are an infinite number of critical points, I know all of the rest of the critical points lie outside the interval I'm considering here. So in terms of me testing points, what do I have to test? Well, there's actually a long list of things I have to test here. I have to test each of these critical points and endpoints in the original function. So the endpoint on the left is 0. The first critical point is 0.6057, 0.9661, 2.1755, 3.7463, and then the right endpoint, oh, whoops, forgot one, 2.5369, and then the right endpoint is 4. So I'm going to have to test my function, the original function, not the derivative, the original function at each of these points to determine which is the smallest and which is the largest. All right. So let's put the function in. P of, I'm just going to use x instead of t. P of x is, okay, our original function is right here. It would be 3x plus sine 4x plus 100. And we're only looking at this on the interval from 0 to 4. Okay, I know that my y value is up at 100, so I'm going to change my window real quick. I want y to go up to at least 100. I need to go further than that, actually. Let's go up to 200. Yeah, I mean, most of the interesting stuff's between 100 and 200. So let me do like 80 to, I don't know, what, 120? I'm just trying to get a good view of the graph. Okay, there we go. So here's our graph on the interval from 0 to 4. The initial insect population is 100. It looks like we cap out over here around 112,000 maybe. And I want to create a table where I list all of these values. So the y here would be P of x1. So my first point that I'm testing, so remember here, these are all the points that we're testing. The first point is 0. The second one is 0.6057. And then 0.9661, 2.1755, 2.5369, 3.7463, and 4. And look at how good of a job we did. You can see that I've got the endpoints marked on the graph. And then here's a maximum, there's a minimum, there's a maximum, there's a minimum, there's a maximum. These are all of the values that we just figured out. And the largest of the values, let me write these down real quick. The The largest of these values looks to be this point here. So this is my absolute max. And the smallest of the values, understandably, is the initial population. So there's my absolute min. So you can see here, absolute max at this point, absolute minimum at this point. All right, that was a lot of work on that problem, but cosine, trig functions, they can be a lot of work when it comes to doing these problems because they do oftentimes have infinitely many critical points. All right, so we're going to take a break from the closed interval method for just a second to talk a little bit more about the nature of what it means to have an absolute max or a min, and then we're going to have two important theorems off of that. So here I have a graph, and what I'm asking you to decide, you can answer it has an absolute max and a min, it has a max but not a min, it has a min but not a max, it has neither. What I'm asking you to decide is on this interval, right? So on the interval shown, does the function have an absolute max or min? And I'm assuming it's a closed interval, right? So closed interval, we're including the point here. Closed interval, we're including the point here. On this interval shown, does the function have an absolute max or min? I'll pause for a second, let you think about it, commit to an answer, and then we'll talk about it. All right, if you haven't committed to an answer, you should do so. Let's talk about absolute min. Absolutely, the absolute minimum is over here at the left endpoint. So this is what, 0.2. So negative 1, negative 1.2, negative 1.4, negative 1.6, negative 1.8, let's say. So, you know, at negative 1.8, whatever the left endpoint here is, you have an absolute minimum. So we have an absolute minimum at this point because we're assuming closed interval here. It looks like the absolute maximum is 2. However, there's an open circle here. The closed circle here is also incredibly important for the same reason. If I had said these were not closed intervals, then this function would have neither. Because it turns out it doesn't have an absolute max. Think about it this way. If you're telling me the function has an absolute maximum at 2, 2 must be a y value on the graph, and it's not. Well, then you say, well, surely it has a max. And I say, well, no, it actually doesn't, because what is the largest y value that you can list? If you tell me the largest y value is 1.9, then I'm going to tell you it's 1.99. Then you can come back and say it's 1.999. I can say it's 1.99999, and we can keep doing this dance forever. We're approaching 2, but we never get to 2. There is no largest value. So the correct answer here is that the function has an absolute minimum, but no absolute max. And if you thought about this being an open interval, it turns out it would have neither. If this is an open interval, it has neither. Because the same argument applies here. We're approaching 0, so you would say, oh, well, 0 is the absolute min. And I would say, well, 0's, if it's open, we don't actually get to 0. So what's the smallest value to the right of 0? Well, there is no smallest value to the right of 0. If you tell me it's 0.01, I'll tell you it's 0.001. And then you'll say, no, it's 0.0001, and we'll go back and forth once again. So the idea of closed intervals is very important to the concept of whether or not you have an absolute minimum or maximum. The other thing that's important is whether or not we include points where you have discontinuities like this. You can oftentimes, at a discontinuity, you can have a point that you can have just values where absolute maximums don't exist on those intervals. So open interval versus closed interval is an important question. And the other really important question here is, do you have any discontinuities? So this example can kind of be summarized with the following problem. And then we're going to have a theorem right after this. So we've got this function. The derivative of this function is 4x minus 20. If we set it equal to 0, you can see that when x is 5, we have a critical point. And if we look at the endpoints, we're on the interval from 1 to 11. So if I test the values at x equal to 1, 5, and 11, I'll know everything I need to know about maxes and mins for this function on these intervals. Starting with at 1, if you plug 1 into the function, you get 2 minus 20 is negative 18, so that would be 532. If you plug 5 into the function, 5 squared is 25, 50, 50 minus 100 would be negative 50, so you'd have 500. And if you plugged 11 into the function, I'm going to need Desmos to help me with that one. Don't want to do that one on the top of my head. So you would have 211 squared minus 20 times 11 plus 550, so 572. All right, so you'd have 572 at the right endpoint. This would make you think that this is the absolute max, and it would make you think that this is the absolute min. However, let's talk about it based on whether or not we have open intervals or closed intervals. So if it's a closed interval, we just did closed interval method, so we know that the max is at 11,572, and we know the min is at 5,500. No big mystery there. That's what we've been doing. What if I make both endpoints open? So if I make both endpoints open, then we can't actually get to the number 572, but we're approaching it the whole way. So this is like me asking, what's the next largest number less than 572? There's not one. You might say it's 571.9. I'll say it's 571.99, and so on. So here we have a situation where there is no absolute max on this interval if we don't include the right endpoint, but we still have the minimum because it's on the inside of the interval. It's okay. And then here, if we add 11 back in, even if we keep 1 open, 1 is not the smallest value. 1 is not an extreme value. So this is the same as the original problem. We have our max back because we've included the point at 11, and our min is on the interior of the interval, so it's not affected by open or closed. So it makes a difference when it comes to closed interval method, whether or not you're dealing with a closed interval or not. You might cease to have a maximum or a minimum if the maximum or minimum is at one of the endpoints and you disallow that endpoint. All right. So all of the examples that we just looked at can be summed up into something called the extreme value theorem. Now, the extreme value theorem says that if you have a continuous function on a closed interval, then that function must always have an absolute max or a min on the interval. A picture of this, I think, will help. The important thing to note here is the hypothesis or the assumption, which is that the function is continuous. I don't have any jump discontinuities or anything like that. So here's just sort of a graph to kind of help you wrap your head around what this is saying. Suppose we have some sort of function defined on the interval from a to b. So I don't care what this function looks like. You can draw any continuous graph that you want. So it can start here, it can go up, it can go down, it can do all of this, whatever. Okay? So there's your graph, there's your function. What this interval says is there must be somewhere on the interval that you have an absolute maximum, a min. And those are the y values that we're looking at. So the minimum looks to be here. And your maximum looks to be there. And what this theorem says is that both of those x coordinates, so I'll call this C1 and C2, have to lie somewhere on the interval. It could be at the endpoint like this one was, but these two values have to be somewhere on the interval. This is C, for the purposes of the theorem, this is C and this is D, so this would be f of C and f of D, right? So these are the y values, and the x points that correspond to them, C and D, must lie somewhere on the interval from A to B. This is only true if the function is continuous. The graph that we looked at previously where we had that jump discontinuity proves that if you have a jump discontinuity, you might not have an absolute maximum or minimum on your interval. So this is the extreme value theorem. It tells us that closed interval method will always work in finding absolute maximums and minimums. All right, related to that is something called Rolle's theorem. What Rolle's theorem says is, it's kind of a fun theorem to think about. Suppose that you have a function and it's defined on a closed interval. So the important hypothesis here is 3, and that is the starting point and ending point of the interval are the same. So you have a situation where the function starts here at f of a, and it ends over here at f of b, but f of b and f of a are equal to each other. The function is continuous, which means there can be no gaps. The function is differentiable, which means there cannot be any corners. If I have to connect this point to this point, and I can't have a corner, and I can't have a jump or a gap, then there must be some place where the derivative is 0 on the interval. Think of it this way. Let's suppose that you start down. If you start down, so if you come out of the point A and initially you're going down, somewhere you have to come back up. So there is the point C where f prime of C is 0. You say, okay, well, what if I started to go up? Well, what if I started to go up? There must be some point where you have to come back down. And at that point where you start to come back down, there's a place where the derivative is 0. Well, you say, well, I'm not going to go up or down. I'm just going to go straight across. Well, if you just go straight across, that's the easiest case of all, because if you just go straight across, then every point on the interval, every point on AB has derivative equal to 0. So in every case, there is some number on the interval where the derivative is 0. And so as long as you have a continuous differentiable function where the starting point and the ending point are equal to each other, there's some place on the interval where the derivative is 0, because there's some place on the interval where you leveled off to come back down, or leveled off to come back up, or you were level the whole way. One thing I should say about this particular problem is we're going to use this in the next problem. And basically all we're going to do is take this picture and twist it. Okay? So let me explain. The next theorem is something called the mean value theorem. It assumes that your function is continuous and differentiable, just like Rolle's theorem. Except it says that there's some point on the interval where the tangent line at that point has the same slope as the secant line connecting the endpoints A and B. So let me show it to you this way, and since I'm on my iPad, this is actually really easy to do. All right, so suppose we have some function, and I'm going to use Rolle's theorem, and I'm going to do a Rolle's theorem graph, so I don't care what this graph looks like. So there's my Rolle's theorem graph, and according to Rolle's theorem, there was at least one point. We actually ended up with 2. This point here, and this point here. Where the derivatives were 0, right? So at both these points we had a derivative of 0. Okay, what if I take this graph, I'm going to get rid of the axes for a second so all I can see is the function. What happens if I take this graph and I tilt it? Let's take this and tilt it. Maybe make it look like that. Now I'm going to reintroduce my axes. So this was at A, this was at B. Okay? Now, what I want you to look at here is the line between the two endpoints. So this line here. This line is what we call the secant line. The secant line has slope, the average rate of change of the function on the interval, so its slope is f of b minus f of a over b minus a. Rolle's theorem, the horizontal line in Rolle's theorem, has slope 0, and it causes the maximum and the minimum here to also have slope 0. In other words, all three of these match. What you can see here is that whatever the secant line is here, if we apply Rolle's theorem, this point and this point, since all of them got tilted by the same degree, the slopes of these two lines must be the same as the slope of this line. So what the mean value theorem is saying is this point here, which I'll call C, and this point here, which I'll call C, at those points, so at this point, the derivative at that point matches the average rate of change on the interval. You know, mean value theorem also has a much better explanation in terms of just real world sensibilities here. This is saying that if you have a function and you have a starting point and an ending point, then whatever your average on that interval is, you must attain that average at some point. So think of it this way. I'm traveling by car from Austin to Dallas. I'm assuming that my path is continuous, which means I don't teleport. Safe assumption. I'm assuming it's differentiable, which means I don't get into a wreck or have some sudden change of direction. Also pretty reasonable. So I'm traveling by car from Abilene to Dallas, and I get done. I take the total distance I traveled divided by the total time. I get my average speed. So I know what my average speed is along the route. Let's say my average speed to Dallas is 60 miles an hour. What mean value theorem says is there must have been somewhere on the trip that I went exactly 60 miles an hour. Think of it just like Rolle's theorem. If I have an average of 60, you can't have an average of 60 by having speeds less than 60, right? So you have to have at least some values that are above 60. Well, now if you have some values that are above 60, you have to have some values that are below 60 so that the average is 60. Well, if you have numbers above 60 and numbers below 60, and you graph the speed function, then the speed function is continuous here, so you can't get from numbers below 60 to numbers above 60 without passing through 60 exactly. So it's just like Rolle's theorem, but it's applied to the derivatives of my function rather than the function itself. And so that's the basic idea here, is you can't have an average rate of change on an interval without experiencing that rate instantly somewhere on the interval. If you have an average rate of change on an interval, the instantaneous rate of change equal to that must appear somewhere on the interval. So let's actually prove this. It's an important result. It's worth our time to prove it, and the proof is kind of cool. So here's what I want us to do with the proof of this result. I want to introduce a new function. So I'm going to let the function g of x be equal to f of x minus, and I think you'll recognize what's going on here pretty quick. So hopefully you recognize this. This is the tangent line to the function f of x at the point A. That's what g of x is. So this is the secant line. I'm introducing the secant line. Okay, so g of x is the secant line. One of the things that you notice immediately about this is that g of a is equal to f of a, and g of b is equal to f of b. You can instantly see it if you plug in x equal to a, that is 0, so you get f of a. And if you plug in b, b minus a cancels with b minus a, so you have f of b minus no, sorry, this would be f of a. F of a. So if you plug in b, right, you get f of b minus f of b minus f of a over b minus a times b minus a. Well, those cancel, and then f of b minus f of b, those cancel, leaving you with the negative of the negative f of a, so you just get f of a. The point I'm trying to make is the function g has the same starting point as it has ending point. Okay? The function f is assumed to be, so if you look at mean value theorem, the function f is assumed to be continuous and differentiable. So because f is continuous and differentiable, then so is g, because g is built off of f, and the function x, which is continuous and differentiable. So I know g of x satisfies Rolle's theorem. It has the same starting point as ending point, and it is continuous and differentiable on the interval. Because of that, if I look at where the derivative of each of these is, so take the derivative of g, you take the derivative of f, this is just a number, this is the slope. So the derivative of x, which is linear, is just the slope. And remember what Rolle's theorem says is there must be some value x on the interval where the derivative of the function, so g satisfies Rolle's theorem, so the derivative of g should equal 0 somewhere on the interval. So g prime of x is equal to 0 for some x in the interval ab. So what this means is for that value of x, f prime of x must equal f of b minus f of a over b minus a. That's the only way that this term is 0 is if this equals this for some x in the interval as well. And this is what the mean value theorem concludes, is that such a value must exist. All right, so last example for the day, we're going to take a look and try to find all of the points that are guaranteed to exist by the mean value theorem. So here we have a function x cubed plus 2x squared minus x. We're looking at this on the interval from minus 1 to 2. The derivative of this function is 3x squared plus 4x minus 1. And we're trying to look at the mean value theorem. Remember, the mean value theorem is about the average rate of change. So the average change on the interval from minus 1 to 2 is f at 2 minus f at negative 1 over 2 minus negative 1. So if you plug in, let's see, f of 2, f of 2 minus f of negative 1, this would be 12 over 2 minus negative 1 is 3. So plugging in 2, we're plugging into the original function. 2 cubed is 8, plus 2 squared is 4, plus 2 is 8, so 16 minus 2 is 14. And then if you plug in negative 1 will give you negative 1, negative 1, so it'll give you 2 total there. And 14 minus 2 is 12 over 3, so this is 4. So I know my average rate of change on the interval is 4. So mean value theorem says somewhere on the interval, my derivative must be 4, right? Somewhere on the interval, the derivative must be 4. So let's set the derivative equal to 4 and figure out where that happens. So we're going to solve for x. So since this is quadratic, it's not too bad. I can subtract the 4 over, in which case I get this quadratic function. Trying to figure out where a quadratic function is equal to 0, which means I'm finding the roots of the quadratic function. So you use quadratic formula here, opposite of b, plus or minus the square root of b squared minus 4ac, so 4ac all over 2 times a. And if you simplify that correctly, you should get 2 points. So these are my 2 values. The first value here is approximately 0.7863, and the other value is negative 2.1196. So there are 2 places where this function's derivative has value 4. I'm guaranteed that one of them, at least one of them, maybe both of them, but at least one of them has to be on the interval. So if we're looking at negative 1 to 2, this point's not on the interval, but this point is. So this is the point that's guaranteed to exist by the mean value theorem. All right, that brings a conclusion to what I'm sure is a very long lecture. Thank you for hanging with me on this one. This is section 4.1 and 4.2. It's a lot going on in those 2 sections, a lot that we'll come back to. You need to have memorized mean value theorem, Rolle's theorem, extreme value theorem, and one more, Fermat's theorem. So those 4 theorems need to be memorized. They will play a major role on exam 3. You need to know extreme value theorem, Rolle's theorem, mean value theorem, and Fermat's theorem. Those 4 theorems. Commit them to memory. All right. Hope you all have a good Easter break. I'll talk to you after the break.